All right, deep dive time. Get ready because we're going to untangle Banach spaces and those things called projective tensor products.
Yeah, jumping into a pretty abstract area of math, you might think, but it's actually behind some really concrete stuff, surprisingly.
Right. Like Banach spaces doesn't exactly sound like everyday stuff, but this is serious stuff. It's the foundation for data science, machine learning, even quantum mechanics uses these principles.
Yeah, it's true. So at the core, Banach spaces are really a way to understand spaces that could have infinite dimensions.
But got to unpack that. Infinite dimensions. So for people who haven't thought about that lately, picture like your typical coordinate plane, the X and Y axis from school, right? Now, imagine you could just keep adding axes, not just Z, but countless axes going into dimensions we can barely imagine. That's the kind of space we're dealing with here, and Banach spaces give us the tools to deal with that.
And within these infinite dimensions, we can do some cool stuff. Imagine you take two of these Banach spaces, and instead of just adding their dimensions, you kind of weave them together like their very fabric is being intermingled. That's what we're doing with projective tensor products.
Weaving spaces together sounds like some kind of math tapestry. But why does it matter how these spaces are woven?
Well, think of it like this. The way we combine them, the rules, they totally change what the result is like, the properties of that projective tensor product. It's like combining ingredients. You can get something amazing or, well, not so much.
So the weaving matters. Okay, but what about this whole smoothness thing? Can a mathematical space even be smooth?
Good question. Shows how we use everyday words for abstract ideas. When we say smooth Banach space, we mean no sharp corners, like imagine a billiard ball, perfectly round.
Gotcha. No jagged edges in this math world.
Oh.
How does that smoothness play into the whole projective tensor product thing, though?
Now that's where it gets really interesting. Turns out the smoothness of the original spaces, it can actually predict how certain points in that final woven space the product will behave.
Okay, hold on. We're talking about specific points in these woven spaces, right?
Yeah.
Not just any points, but ones with a special property called, get this, strong subdifferentiability, or SSD for short.
And these SSD points, they're like the well-behaved citizens of this math world. They make it easier to predict how functions will act within that space.
Got it. So SSD points bring some order to the chaos of infinite dimensions, but how do we even know where to find them?
That's where the smoothness of the initial Banach spaces comes in. The research we're looking at really digs into how that smoothness of one space, along with another property called the modulus of convexity in the other space, can determine if certain points in that final product will be those nice SSD points.
Okay, so we have smoothness. Now we're adding modulus of convexity. This is getting layered like a math cake.
Haha. Good analogy. And just like a cake, the right combo, in this case, smoothness and modulus of convexity, can give you a very specific and often good outcome, those well-behaved SSD points.
Now that's what gets me excited. But break down this modulus of convexity thing. What is it, and why do we care how curved a math space is?
Okay, imagine a basketball in a dinner plate. The basketball all curved, it has higher modulus of convexity. The plate, pretty flat, lower modulus. This curvature, combined with the smoothness of the other Banach space, they're key to what the final projective tensor product will be like.
So we've got these mathematical ingredients, smoothness and modulus of convexity, interacting in this fascinating way to influence the properties of the projective tensor product. But don't think for a second that this is just about some esoteric mathematical recipe. This stuff has real-world implications.
Absolutely. One of the most exciting aspects of this research is its potential to impact fields far beyond the theoretical realm of pure mathematics. We're talking about advancements in areas like data analysis, signal processing, even the development of more efficient algorithms.
Okay, so we're not just talking about numbers on a chalkboard here. This has the potential to change the way we interact with and understand the world around us.
Precisely. Imagine being able to analyze complex data sets with greater precision or optimize algorithms for faster and more accurate results. That's the kind of impact this research could have.
That's incredible. But let's bring it back to those SSD points for a moment. They seem to be the key players in this mathematical drama. The more we have of them, the more predictable and well-behaved our projective tensor product becomes. But how do we know if we're dealing with a space that's teeming with SSD points, or if they're as rare as hen's teeth?
That's a crucial question, and as you might expect, it all comes back to the properties of the original Banach spaces we're combining. The research found that certain types of Banach spaces are more likely to produce projective tensor products with an abundance of those desirable SSD points.
So it's like some spaces are just naturally inclined to be more well-behaved than others.
You could say that. One intriguing finding was that when you combine a specific type of Banach space called C0I with a smooth finite dimensional space, the resulting projective tensor product often exhibits a remarkable degree of predictability and order a testament to the prevalence of SSD points.
Okay, time for a quick knowledge check. We've encountered this mysterious C0I space before. Can we have a little refresher on what that's all about?
Of course. Imagine a list of numbers where, as you go further down the list, those numbers gradually approach zero. They get smaller and smaller, fading away into the mathematical distance. That's the essence of C0I.
So it's like a space where numbers eventually just fade to black. I'm starting to see why combining that with a smooth, well-defined space might lead to a more predictable outcome.
Exactly. What's remarkable is that even though CU0I is quite distinct from those other spaces we've discussed, the same principles of smoothness and modulus of convexity still hold sway in determining the prevalence of SSD points within the resulting projective tensor product.
It's like there's a universal law of mathematical spaces at play here. No matter how different these spaces may seem on the surface, these fundamental properties continue to exert their influence.
It's a testament to the interconnectedness of mathematical concepts, but here's where things get even more intriguing.
You know, I live for these intriguing turns in our mathematical journey.
The research delves into a particularly fascinating concept, the LPP property for bilinear mappings. It's a bit of a mouthful, I know, but bear with me.
We're not afraid of a little mathematical jargon here. Our listeners are ready to dive deep into the weeds.
Excellent. This LPP property is like a VIP pass into a deeper understanding of how operators behave within these projective tensor products.
Okay, I'm picturing a velvet rope and everything. So what makes this LPIP property so special?
Well, the research suggests a tantalizing connection between a Banach space having lots of SSD points and this LPP property holding true for the spaces being combined. It's like discovering a secret tunnel between two seemingly separate mathematical castles.
So the more well-behaved our points, those SSD points we've come to know and love, the more likely this LPIP property is to be true for the spaces we're working with.
Precisely. It hints at a deep and potentially fundamental link between these concepts, one that researchers are only beginning to unravel. And this discovery opens up a whole new world of questions and avenues for exploration.
You know what they say about one mathematical door opening as another closes? Or something like that. What are some of the burning questions that this research has sparked?
Well, for starters, the research primarily focused on specific types of Banach spaces, like those OOP spaces in the intriguing C0I, but the vast universe of Banach spaces extends far beyond these examples. So a natural question arises. Do these same principles of smoothness, modulus of convexity, and their connection to SSD points hold true in other Banach spaces?
It's like we've only explored a tiny island in a vast mathematical archipelago.
Exactly. And even within the spaces we've explored, there's so much more to uncover. We've talked about the importance of SSD points, but how prevalent are they really? Are they relatively common, or are they like finding needles in a haystack of mathematical possibilities?
These are the kinds of questions that keep mathematicians up at night, aren't they? I can practically hear the sound of furiously scribbled equations echoing through the halls of academia. But before we get too lost in those hypothetical hallways, there was one more intriguing concept from the research that I want to touch on, the multiple point SSD condition.
Ah, yes. Now we're venturing even further into the fascinating world of projective tensor products. Instead of just considering the behavior of individual points, this condition encourages us to look at entire collections of points within our space.
So it's like we've zoomed out from a single billiard ball to observing the entire pool table.
Precisely. And we're asking, under what conditions can we guarantee that all of these points will exhibit that same desirable SSD behavior?
Because one well-behaved point is great, but a whole collection of them, that's like hitting the mathematical jackpot. But I have to admit, my brain is starting to feel a bit like a stretched tensor product at this point. Can you walk us through why this multiple point SSD condition is so significant? What doors does it unlock in our understanding of these spaces?
Of course. It turns out that this condition is intimately linked to our ability to approximate certain complex elements within the projective tensor product.
Okay, hold on a second. We're talking about approximations now. How does that tie into the grand scheme of things?
Think of it this way. The objects that inhabit these tensor product spaces can be incredibly complex, often too intricate to grasp directly. So mathematicians employ a powerful tool approximation to represent these complex objects using simpler, more manageable ones.
So it's kind of like using a connect the dots picture to get a sense of what a larger, more complex image might look like.
Precisely. And what this research reveals is that the presence of this multiple point SSD condition can significantly enhance our ability to construct accurate approximations for those complex elements within the projective tensor product.
So the more well-behaved our points are, the more likely we are to accurately represent those complex objects in our woven mathematical tapestry.
That's the essence of it. This condition provides a powerful lens through which we can view and, importantly, manipulate those intricate structures that reside within the realm of projective tensor products. And what's even more exciting is that this is just the tip of the iceberg.
Don't tell me there's more. My brain is already doing backflips trying to keep up with all these mind-bending concepts.
That's the beauty of mathematics, isn't it? Every answer often begets a multitude of new and even more intriguing questions. This research has opened up a Pandora's box of possibilities, with researchers eager to explore the ramifications of these findings in other types of Banach spaces, and to delve deeper into the connections between smoothness, modulus of convexity, and the ever-elusive SSD points.
This has been quite the deep dive. We've gone from what seemed like a simple concept smoothness to exploring the depths of Banach spaces, projective tensor products, those intriguing SSD points, and now this mind-boggling multiple-point SSD condition. I feel like we've scaled a mathematical mountain and caught a glimpse of a vast and uncharted territory stretching out before us.
And that's the beauty of it all, isn't it? The journey of mathematical exploration is never truly over. There's always something new to discover, some hidden connection to unearth, some seemingly impenetrable problem waiting to be cracked wide open.
So for our listeners who are feeling that spark of curiosity, that desire to explore further, where should they direct their mathematical compasses?
Well, the paper we've been dissecting today is an excellent starting point. It lays the groundwork for a whole new avenue of research in the world of functional analysis. But the real adventure begins when you start asking your own questions.
What about other types of Banach spaces? What other surprising connections are lurking out there waiting to be discovered? What other real-world problems might be tackled using these powerful mathematical tools?
The possibilities are as boundless as the spaces themselves. And who knows, maybe one of our listeners will be the one to make the next groundbreaking discovery in this exciting field.
Now that's a thought-provoking note to end on. So until next time, fellow explorers, keep those minds curious and keep diving deep. So just to recap, we've been on this journey seeing how individual Banach spaces, like their smoothness and how much they curve, that modulus of convexity, it really affects the whole projective tensor product. And we've even touched on how this math, which seems so out there, could actually change how we analyze data, make better algorithms, all that.
And that connection, right, between all those well-behaved SSD points and that, as we call it, VIP path to deeper understanding, the LP, all-pay property, it's like these ideas are talking to each other in the language of math.
Secrets we're just starting to pick up on. And speaking of secrets, you mentioned something really interesting about that multiple point SSD condition, how it helps us approximate the really complex stuff, those elements within the projective tensor products, right?
Exactly. It's one thing to approximate one complex thing, but imagine trying to understand a whole bunch of them at the same time. That's where this multiple point SSD condition comes in. When that works out, it's like getting a super high resolution look at everything, seeing even the tiniest details of these collections.
So it's not just connect the dots anymore. It's like upgrading to a full-on high-definition picture. We see those complex mathematical objects so much clearer.
You got it. And that's huge. This condition, it's basically giving us the tools to actually work with this complexity, analyze it better, even manipulate it in ways we couldn't before.
We're not just looking at the surface of these math spaces anymore. We're getting our hands dirty with how they're actually built.
That's what makes this research so exciting. It's not just theorems in some math book. It's changing what we thought was possible. These tools could change how we understand any system with lots of complexity.
And that reminds us, math might seem like its own thing, but it's woven into everything around us, right? It's the language of the universe, from tiny particles to giant galaxies. The more we get that language, who knows what secrets we can unlock, what we can do with it.
Couldn't have said it better myself. And who can even guess what other mysteries are hiding in math? What other abstract thing will turn out to be important for how we see the world? That's the best part. The journey doesn't really end.
What a thought to wrap up on. Well, that's our deep dive for today, folks. We traveled through those fascinating Banach spaces, got tangled up in projective tensor products, and saw how powerful those SSD points really are. I don't know about you, but my brain's full of new ideas. A huge thanks to you, expert, for guiding us through all that. And to everyone listening, stay curious and keep on exploring.
Okay, so get ready to dive into the world of Banach spaces, but don't worry, we're going to make this fun. Okay. Today we are looking at a paper with a very long title called New Examples of Strongly Subdifferentiable Projective Tensor Products. I know, right? A mouthful.
It's a bit of a tongue twister, but trust me, the concepts are way more exciting than the title.
That's what I'm counting on. Okay, so what is the big idea here? What is this paper actually about?
Imagine like you're trying to describe the bumps and curves of a shadow, but the object casting that shadow exists in like a million dimensions. That's kind of what we're dealing with. This paper is diving deep into how smooth or bumpy certain shapes are in these really high-dimensional spaces called Banach spaces.
Okay, I can vaguely picture that. And the smoothness idea, that's where the strong subdifferentiability or SSD comes in, right? Why does that even matter?
You got it.
Yeah.
SSD is essentially a way to quantify that smoothness. And what's fascinating is that this property can have huge implications for how we solve problems in fields like optimization, you know, like finding the best solution out of a ton of possibilities.
So like if you're trying to optimize a flight path, knowing how smooth the space of all possible routes is actually helps you find the best one more efficiently.
Exactly. This paper focuses on specific types of spaces called projective tensor products. They sound super niche, but they're actually incredibly common in math. Think of it this way. You need three numbers to describe a location in space, right? Latitude, longitude, and altitude.
Right, like those 3D coordinates we learned about in school.
Exactly. Projective tensor products help us generalize that idea to describe points in spaces with way more than 3 dimensions.
Okay, so instead of points on a map, we're talking about points in some theoretical hyperspace.
I like that. And just like with your map example, the properties of the space itself, like its smoothness, or SSD, affect how we can navigate and analyze problems within that space.
So what did this paper uncover about SSD in these projective tensor products? Did they find some secret mathematical shortcut?
Well, they focused on a specific type of projective tensor product. It's denoted by OPI. I know it looks like a jumbled mess of symbols, but bear with me.
Oh, don't worry. My brain already short-circuited just hearing that. Can you break it down for us? What are those symbols actually telling us?
Of course, think of OPI as a way to represent a whole bunch of numbers, maybe even an infinite number. It's like a container for these numbers. And Y, that represents another space, but this one is smaller. It has a fixed finite number of dimensions.
Okay, I'm sort of with you so far. Two different spaces, one with a bunch of numbers, the other with fixed dimensions.
Right. And that symbol in the middle, that's the tensor product part. It's the mathematical operation that combines or weaves together those two spaces.
So they're taking these two spaces and basically smashing them together to create a new, even more complex one. Why would you do that? What's the point of combining them?
It's like combining ingredients to create a new recipe. Sometimes the properties of the combined space are more interesting or useful than the individual ingredients on their own. And in this case, the authors were particularly interested in when this combined Uri space would have the property of strong subdifferentiability. Remember, that's our smoothness measure.
Right, right. So did they figure out when these Frankenstein spaces end up being smooth? What makes them that way?
They did. They found that it all depends on a couple of key factors. First, the p-value in OPI plays a big role. Think of p as a knob that controls how curvy that space is. The higher the p-value, the smoother the OP space becomes.
So it's like adjusting the resolution on a computer model. Higher p means a higher resolution, smoother curves, less pixelation.
That's a great way to think about it. The second factor is the type of smoothness present in the Y space. It's not enough for just one of them to be smooth. They have to complement each other in a very specific way for the combined space to be strongly subdifferentiable.
Okay, so it's all about finding the right combination of smoothness between those two spaces, like finding the perfect harmony between two instruments.
Exactly. And the paper lays out the precise conditions for when that perfect harmony occurs. They proved that if p is bigger than 2 and the Y space has a specific type of smoothness, something called a modulus of convexity with power type q less than p, then boom, you've got strong subdifferentiability in the combined space.
Whoa, okay, so there's a very specific recipe for creating these smooth spaces. What makes this discovery so interesting? Why does any of this even matter outside of theoretical math? This might be my inner engineer talking, but I love when these seemingly abstract math concepts have these very tangible applications. It's like, okay, so how does this smoothness discovery actually play out in the real world?
You're right to be thinking about applications. One area where this research could have a huge impact is in optimization problems. We're talking about anything from designing more efficient algorithms for machine learning to optimizing logistics and supply chains.
So we're talking about making those algorithms smarter by understanding the underlying geometry of the problem, right? That's wild, like having a secret weapon to navigate through all the possible solutions.
It's more like having a better map. By knowing the smoothness properties of these complex spaces, we can develop algorithms that find the best solutions faster and with less computational power.
That's huge, especially in fields like machine learning where you're dealing with massive data sets and complex models. Any improvement in efficiency is a game changer.
Absolutely. And what's even more fascinating is that this paper actually connects these abstract spaces to ones we encounter in other areas of math, like statistics. They talk about something called LQ spaces.
Okay, I've definitely seen that one before. Remind me though, where do those pop up? What's so special about them?
You'll find LQ spaces all over the place in statistics and probability theory. They're used to describe how things are distributed.
Well,
Think about things like the heights of people in a population, the spread of data points in a data set, or the possible outcomes of a random event.
right. So are they saying there's a link between these statistical spaces and the smoothness we've been talking about in projective tensor products? That seems like a bit of a leap.
It does seem like a leap, but that's what's so exciting. The paper shows that the relationship between the smoothness of those different spaces, the spaces from before, and these LQ spaces, directly affects whether that crucial strong subdifferentiability property holds in the combined tensor product space.
It's like they're building a bridge between these different mathematical worlds. And knowing how those worlds are connected could lead to some really unexpected insights.
Precisely. And those bridges are incredibly valuable because they allow mathematicians and scientists to transfer knowledge and techniques from one area to another. This kind of cross-pollination of ideas is often where the most exciting breakthroughs happen.
Now, there was this other part of the paper that really caught my eye. They mentioned a transfinite version of their theorem. To be completely honest, I'm not even sure what that means.
Alerts. Don't worry, you're not alone. Transfinite sounds intimidating, but it's actually a very elegant concept. Imagine constructing an infinite tower of these projective tensor products, each level built on top of the last, getting progressively more complex.
Okay, I'm trying to visualize this infinite tower of mathematical spaces. Go on.
The transfinite version of their theorem essentially says that their findings about strong subdifferentiability still hold true, even as you climb infinitely high up that tower.
So instead of just analyzing one specific projective tensor product, they're showing that their results apply to an entire infinite family of these spaces. That's some next level math right there.
It is, and it demonstrates the power of abstract mathematics to uncover deep patterns and relationships that hold true, even in incredibly complex scenarios.
Yeah.
To prove this transfinite version, they introduce a condition called the LPT condition.
Ah, yes, more mysterious symbols. But I have a feeling you're going to break it down for us and make it crystal clear, right? What does this LPAIP condition actually tell us?
You're right, it does look cryptic, but the idea behind it is actually quite intuitive. Imagine you're trying to draw a perfect circle, but you're only allowed to use straight lines. You can get closer and closer to a perfect circle by using more and more lines, but there will always be a tiny bit of error, right?
Right. You can keep adding more sides to your polygon, but it'll never be a truly smooth circle. There will always be those tiny corners.
Exactly. That's a great way to think about it. This LPOP condition is all about exploring the limits of how small that error can be when you're trying to approximate something in these complex, infinite dimensional spaces.
So it's about finding the best possible fit within a certain level of precision. It's like those draw circle games at carnivals. You're never quite sure how much wiggle room you have.
That's a perfect analogy.
Yeah.
And what they found is that the LPAP condition is intrinsically linked to the smoothness of the spaces involved. Even in these incredibly complex, infinite dimensional spaces, the relationship between smoothness and the ability to find good approximations remains crucial.
This is blowing my mind. They've linked together smoothness approximations and these infinite towers of spaces. But how does this LPT condition actually play into their transfinite theorem?
That's the real beauty of this research. They use the LPP condition to demonstrate that even as you climb higher and higher up, that infinite tower of projective tensor products, meaning those spaces become increasingly complex, you can still find incredibly good approximations.
So even though those spaces are mind-bogglingly complex, this underlying principle of finding the best fit still holds true.
Exactly. And what determines whether or not you have that coveted strong subdifferentiability in these ever more complex spaces, it all comes back to the relationship between the smoothness of those approximations and the smoothness of the original spaces themselves.
Wow, so even in the infinite mathematical universe, this paper manages to find a sense of order and structure. It's like they're mapping out the cosmos of mathematical spaces, pinpointing those special spots where strong subdifferentiability thrives.
That's a beautiful way to put it. It really highlights how even when mathematicians are working with incredibly abstract concepts, those concepts are often rooted in more familiar ideas like approximation smoothness and the idea of finding the best fit.
It's like they're revealing the hidden patterns and connections that underlie the entire structure of mathematics. And to think it all started with a question about smoothness in these high-dimensional spaces.
Exactly. And as we've been discussing, these seemingly abstract discoveries can have far-reaching implications in fields that impact our everyday lives.
Speaking of those implications, I'm curious to hear more about how you see this research potentially influencing fields like machine learning and optimization. It seems like we're just scratching the surface of what's possible. For our listeners who might be thinking, okay, this is all fascinating, but what's the takeaway for me? What would you say is the biggest implication of this research? How could this impact someone who's not a mathematician?
That's a great question. I think this paper gives us a powerful reminder that even the most abstract mathematical concepts often have roots in more familiar ideas and can lead to real-world breakthroughs. We started with this idea of smoothness in high-dimensional spaces, something that might seem purely theoretical, and we've ended up talking about statistics optimization and the potential for more efficient algorithms.
Right. It's like this paper is revealing the hidden connections between these different areas of math, and those connections have the potential to ripple out and impact all sorts of fields.
Exactly. Think about how much of our modern world relies on optimization. Everything from financial modeling to online shopping recommendations to medical imaging analysis. By understanding the underlying geometry of these problems, as this paper helps us do, we can potentially develop smarter, faster, and more efficient solutions.
That's pretty mind-blowing when you think about it. We're talking about unlocking new levels of efficiency and problem-solving capabilities just by delving into the abstract world of shapes and smoothness in these high-dimensional spaces.
It's true. And while the applications of this specific research are still being explored, it highlights a crucial point. The pursuit of pure mathematics, even when it seems far removed from our daily lives, can lead to incredibly practical and impactful discoveries.
Absolutely. Now, before we wrap up, I have to ask, did anything in this paper spark any particular research interests for you? Any threads you're hoping to pull on in your own work?
There's one bit that really stuck with me. The paper talks about spaces where the set of strongly subdifferentiable points is dense. It's a bit technical, but the idea is that within these complex spaces, there are these pockets of perfect smoothness distributed everywhere.
Yeah. Okay, I think I'm following so far. These dense points of perfect smoothness. What's so intriguing about them?
Well, I'm really fascinated by the possibility that these points could hold the key to bridging the gap between classical and quantum computing. It's a long shot, but the idea that these abstract mathematical properties might help us unlock the potential of quantum computation is incredibly exciting.
Now, that's a thought-provoking idea to leave our listeners with. Always pushing the boundaries of knowledge. That's what we like to hear. Well, thank you so much for joining me on this deep dive. It's been an incredible journey into the world of Banach spaces and strong subdifferentiability.
It's been my pleasure. It's always a treat to dive into these fascinating mathematical concepts and explore their potential implications.
Until next time, keep those brains curious, everyone. Okay, so today we're diving into, well, it's a paper, right? And it's about something called, are you ready for this? Strongly subdifferentiable projective tensor product spaces.
Yeah, that's quite a mouthful.
It's a mouthful, but I think the ideas here are actually way cooler than all that jargon might suggest. So trust us, stick with us.
What's really neat is that it's all about, like how smooth is a mathematical space.
Okay, smoothness and math. I'm gonna need you to elaborate on that a bit for
Sure,
me.
sure. So imagine you have a bowl, right? Like a flat plate, it has zero curvature, but like a shallow bowl, it's got a little bit of curvature, and the deep bowl, you've got a lot, right? And we can measure that bowl-likeness in math, and that's kind of what we're getting at here.
So are we saying that mathematical concepts literally have a shape, like a bowl?
Well, not literally, but
Right.
we can use these geometric ideas to think about them, right?
Yeah.
And what's really cool is that this paper looks at what happens when you combine these spaces, these ingredients, as it were, and how that affects the smoothness. It's like, in a recipe, you're combining different ingredients to get a final product with a certain I don't know, consistency or texture.
Okay, I am all about a good food analogy, so I'm
Yeah.
following you so far. So let's talk about those ingredients. You keep using the word tensor products. What are those exactly?
So tensor products are basically a way mathematicians take different mathematical objects and combine them while still keeping some of their individual uh, characteristics. It's like, when you blend a strawberry and a kiwi together, you get a new flavor, but you can still kind of taste the strawberry and the kiwi.
I am definitely getting a smoothie vibe here. I like it. So this paper is looking at how to make the smoothest mathematical smoothie possible.
In a way, yeah. This mathematician, Abraham Rueda Zoca, he actually found some new combinations of these ingredients, these projective tensor products, that make a surprisingly smooth final product, so to speak.
So he found new mathematical smoothie recipes. That's awesome. But what's the big deal? Why are mathematicians so excited about these smoother combinations? Like, what doors does this open for them?
Well, the implications are pretty huge, actually. Having these smoother combinations gives us better tools for understanding really complex systems. And we're talking about things in physics, in computer science, even in, economics.
Whoa, really?
Yeah.
I never would guess that. So how does the smoothness of some abstract mathematical space translate to something like, I don't know, predicting the stock market or something?
Okay.
The movement of, one tiny particle, right? Now imagine trying to track the movement of millions of those particles all at once, all interacting with each other. That's where these tensor products come in.
So it's like a mathematical net for capturing the behavior of a whole swarm of particles.
Yeah, exactly. And the smoother the tensor product, the more accurately we can describe and model what those particles are doing.
And then we can apply that same principle to other fields, like economics.
Yep. We can use tensor products to model things like financial markets, where you have all these different variables interacting in really intricate ways.
So finding these new smoothie recipes could help us build better financial models. That's amazing.
That's the idea. And the really cool part is how Rueda Zoca did it. He found these clever techniques, like one of them involves taking these infinitely complex spaces and sort of,
Simplifying them.
reducing them into smaller, more manageable pieces that we can actually work with.
Hold on. So he's taking an infinitely complex thing and breaking it down. How is that even possible?
Okay, imagine you're trying to understand how a giant flock of birds moves, right? Instead of trying to track every single bird, which would be impossible, you could focus on smaller groups within the flock. If you notice a pattern in how those smaller groups move, you might be able to figure out something about the whole flock.
Okay, I get it. So he found a way to analyze these smaller bite-sized chunks of the math and then apply what he learned to the bigger picture.
Exactly. And by doing that, he was able to prove that certain combinations will always lead to these beautifully smooth tensor products, no matter what.
Okay, I think I'm starting to get the gist of what he did, but my brain is definitely starting to feel the burn here. Can we back up a sec and talk about how he actually proved that these new combinations are smooth? Like, where do we even begin with proving something like that?
Sure. To really get that, we need to dive a little deeper into this whole smoothness thing, and specifically a concept called strong subdifferentiability.
Hit me with it. But maybe go easy on the jargon this time. Remember, I'm just a humble podcast host over here.
Right, of course. So remember our bowl analogy. Well, strong subdifferentiability basically means that if you were to zoom in on any point on that bowl, it would be perfectly smooth. No bumps, no jagged edges, nothing like that.
So it's not enough for the whole bowl to be smooth. Every single point on the surface has to be smooth too.
You got it. And what Rueda Zoca did was prove that his combinations don't just create smooth bowls, but bowls that are smooth at every single point. And that's huge.
This is starting to sound like a mathematical detective story. We've got smooth bowls, secret recipes, flocks of birds. I'm here for it. But before we get too far, I want to go back to those real-world applications for a sec. You mentioned that this research has implications for things like quantum physics. Can you give me a concrete example of how understanding smoothness in this way actually plays out in a field like that?
Absolutely.
Yeah.
So in quantum physics, we use tensor products to describe the state of quantum systems, which often involve lots of particles interacting in really, really complicated ways.
Okay, so we're back to our particle net, right? Trying to capture all that quantum weirdness.
Exactly. And the smoothness of those tensor products, believe it or not, it directly affects how well we can predict and model how those quantum systems will behave.
So a smoother tensor product means we can get a clearer picture of what's happening in the quantum world.
Precisely. And that has some big implications. Like, think about fields like material science or quantum computing, which relies on understanding these systems. And that's just the tip of the iceberg.
So if I'm picturing this right, a smoother tensor product, it's like we can predict where those quantum particles are going to go with more, I don't know, accuracy, like less turbulence.
Yeah, exactly. It's like having, a clearer lens to view the quantum world and having that understanding these quantum systems better. It's like it's a big deal for stuff like material science and quantum computing.
Okay, you completely lost me at quantum computing, but that's all right. We can save that for another day. So back to the paper, though, this Rueda Zoca guy, you said he used some pretty innovative techniques to to prove what he was talking about, right? And one of them was like breaking down those infinite spaces, but what else?
Well, he uses this thing called the modulus of convexity.
Oh boy, here comes the jargon again.
It's not as bad as it sounds. Just think about our bowl again, right?
Your balls? You really love your balls?
Yeah, it's a good analogy.
Yeah.
So the modulus of convexity basically tells us like how deep that bowl is. A flat plate, 0 depth. A shallow bowl, a little depth, and a deep bowl, well, it's got a lot of depth. What Rueda Zoca did was he basically showed that if you take like a really deep bowl and combine it with a really flat one in just the right way, the result is always going to be smooth.
So it's like adding a splash of flatness to a super deep bowl, and that creates like the perfect mathematical smoothie consistency.
Exactly. And to do this, he used this specific type of space that's called 8 spaces. So like imagine coordinate systems, but they can go on forever.
Infinite dimensions, now we're getting really out there.
But the bowl analogy still works. So these ape spaces, they can be deep or shallow too, and it depends on this value, this p-value. And what Rueda Zoca showed is that if you have a really deep ape space, so large p, and you combine it with like a normal finite dimensional space, the result, it's like it takes on that deep smoothness. It becomes strongly subdifferentiable, just like that.
So like the deepness of the ope space, it just overpowers everything else.
Yeah, kind of. It's like you can't make a really spicy salsa if you keep adding avocado to it. And this is just one part. Remember how he breaks those infinite spaces down? Well, he uses that here too.
Wait, hold on. Now he's slicing up our mathematical bowls.
It's all connected. He basically proves that if this smoothness thing, if it works for all those little finite slices of the bowl, it has to work for the whole infinite thing too.
Okay, that actually makes some sense. It's like, I don't know, you can tell if a giant pizza is good by just trying a few carefully chosen slices. But how do you actually go from those slices to the whole pizza? That's the part that's always gotten me.
He uses this really powerful idea it's called functional analysis. It gets a bit technical, but basically it's a way to connect how those smaller pieces behave to how the whole structure behaves.
All right, we don't have to get into the nitty-gritty today, but I am curious. Like, we've talked a lot about the math, but can you give me an example of where this smoothness property actually matters in the real world?
Sure. Remember our economics example. Think about trying to build like a mathematical model to understand how stock prices change. It would need to factor in like tons of different things, right? And all those things are super interconnected.
Okay, so we're back to our swarm of birds, but this time they're stock prices.
Exactly. And the smoother the tensor product space, the better that model is going to be at capturing all those relationships.
So smoother tensor products, maybe better financial models. Got it. But what about, like, you've mentioned quantum computers earlier, right? What about those?
Yeah, so when we're talking about quantum computers, smoothness, it's really important for how stable and how reliable those quantum algorithms are.
Quantum algorithms. Now there's a whole other mystery.
It is a bit complicated, but just think of it like quantum algorithms. They're like the recipes for those quantum computers. And if the underlying math, if that's smoother, it's less likely that those algorithms are going to have errors or be affected by noise.
So it's all about making the math as smooth as possible to get the best performance out of these quantum computers.
That's a great way to put it. It's all about creating that smooth, stable environment for everything to work properly.
Wow, we've covered a lot of ground. From smooth bowls to quantum computers, who knew? But there's one more thing from the paper I gotta ask about. It mentions this thing called, get this, the LPE, property for bilinear mappings. I'm not even gonna try to say that again. But it seems like this is like another layer to this whole smoothness thing.
Yeah, you're right on the money. It's really about like the specifics of how we guarantee that smoothness. So remember how we talked about tensor products, like recipes blending 2 ingredients together, right? Well, a bilinear mapping, it's like a very specific kind of recipe where the final flavor, it's always directly proportional to how much of each ingredient you put in.
So it's like if I double the strawberries in my smoothie, it's going to be twice as strawberry, but still balanced, right?
Exactly. You're getting it. And so the LLPP property, it's like it tells us that if our recipe, if that bilinear mapping is already making something smooth, there's a way to make it even smoother. Like no matter what we put in, it's always going to blend perfectly, guaranteed.
Okay, but how does this LPP thing connect back to those tensor products and the smoothness we were talking about before?
Well, that's the whole point, right?
Yeah.
This paper, it shows us that if this property, this LPP thing, if it's true for the things we're combining, the spaces, then that tensor product at the end, it's guaranteed to be strongly subdifferentiable. It's going to be smooth all the way down, no matter what.
So like it's a test for our mathematical smoothie recipe. If it passes the LPP test, we know it's going to be good. Smooth.
Yeah, that's a great way to think about it. And get this, Rueda Zoca, he even introduces this like multi-point version of this LPP thing, and it gets even wilder.
Multi-point. Okay, now I'm really lost.
So instead of just looking at one point on our bowl, right?
Yeah.
This multi-point version, it's like looking at a bunch of points at the same time, making sure they all blend together smoothly no matter what.
So every sip of our mathematical smoothie is perfectly smooth, no matter where we dip our spoon.
You got it. And what's cool is he proves that this multi-point thing, it works for certain groups of points. And by doing that, he finds a whole new way to guarantee smoothness for the whole tensor product, even if we don't know that much about the original spaces.
That's pretty impressive. It's like
Yeah.
he's found a way to make the smoothest possible blend, no matter what you throw in there.
And here's where it gets even more interesting. The paper, it kind of hints at this idea that if we just have enough of these smooth points, right, the whole space, it might be like smooth enough for most things, even if it's not perfectly smooth everywhere.
So even if there's a few tiny ice chips in our smoothie, it's still going to be pretty good.
Exactly. And that's what's so cool about this. It's not just about finding the perfect smoothness. It's about understanding how to work with things that might have a few bumps, but still figuring out how to use them.
This whole thing has been pretty wild. Smooth bowls to quantum computers who knew they were all connected. What's the biggest thing you're taking away from all this?
Honestly, the way Rueda Zoca takes these super abstract mathematical ideas and he connects them to real things. Physics, economics, it just shows how powerful math can be for understanding, even shaping the world.
Yeah, I'm with you there. It's like sometimes the most groundbreaking stuff, it comes from the most unexpected places. So listeners, if you're into those hidden mathematical structures, you know, the ones that make up everything, keep those brains buzzing. Because as we've seen today, even something as simple as smoothness, well, it can unlock a whole universe of possibilities.
Ever crack open a research paper and feel like you need like some kind of secret decoder ring just to understand the title?
I know that feeling, yeah.
Well, get ready to decode because today we're diving headfirst into this. New examples of strongly subdifferentiable projective tensor products.
Now that's a mouthful.
It is. But don't worry, that's why you're here. We're going to break down this dense mathematical jungle into a clear path with no PhD required.
Yeah, think of it as your like cheat sheet to sounding really smart at your next cocktail party.
Exactly. So this paper, it dives into these things called Banach spaces, which I don't know about you, but to me that just sounds like something straight out of Star Trek.
They do sound kind of sci-fi, don't they? But they're really just, well, they're specific types of mathematical spaces.
So like mathematical building blocks, but instead of houses, they're using them to build like incredibly complex and abstract concepts.
Yeah, exactly.
Okay, so what are they building with these Banach space blocks in this paper?
Well, they're really interested in this thing called, it's called strong subdifferentiability, often shortened to SSD.
Catchy.
Yeah, super catchy. But it's all about trying to understand the smoothness, or I guess you could say the bumpiness of these spaces. Like imagine you're trying to navigate some landscape in complete darkness.
Okay.
SSD is like, it's like developing this mathematical sense of touch so you can kind of feel your way around and understand the terrain.
So SSD is like giving mathematicians these night vision goggles for these abstract mathematical landscapes.
Exactly, you got it. And to make things even more interesting, they're exploring this smoothness, this SSD, in the context of projective tensor products, which, yeah.
Okay, now you're just using big words to make me nervous again.
I promise, it's not as complicated as it sounds. Think of a tensor product like combining ingredients when you're making a recipe, you know?
Right.
You're taking these two separate mathematical objects and and kind of blending them together in a very specific way. And that specific way is where that projective part comes in.
Okay, so we're in a mathematical kitchen mixing up Banach spaces with this special projective tensor technique.
Gotcha. Now the paper, it's on a quest for new examples, which I'm guessing means other mathematicians have already found instances of these SSD projective tensor products.
Yeah, exactly. They're out there.
So why is finding new examples so important? Well, because each new example is it's like discovering like a new species in this vast, uncharted mathematical jungle.
Okay.
And the more we find, the more we start to understand the underlying principles that govern these really complex mathematical objects.
So it's like piecing together this giant puzzle, and each new example gives us a clearer picture of the bigger mathematical reality.
Yeah, that's a great way to put it. That's exactly right.
So the researchers in this paper, they've unearthed some pretty fascinating examples using a tool called the W-cadet-Klee property, which, and I hate to interrupt, but
Go for it.
you know, for a bunch of mathematicians, they're not very good at like catchy names.
That's true. Yeah, we could use some help in the PR department.
For sure. Okay,
Yeah.
but for those of us who don't speak fluent mathematician,
Yeah.
what does this W-cadet-Klee property, what does it actually mean? What does it do?
Okay, so imagine you're looking at a blurry image, like way too zoomed in.
Mhm.
And as you zoom out, it slowly starts to come into focus, right?
Right?
The W-cadet-Klee property, it's basically a condition that allows mathematicians to do that, to zoom in on these mathematical spaces and study their properties with more and more detail.
So it's like having like a mathematical magnifying glass.
You could say that, yeah. It helps them see the fine details, the subtle nuances of these spaces.
Very cool. So armed with this mathematical magnifying glass,
Mhm.
what did the researchers actually discover? What treasures did they unearth in this mathematical jumble?
Well, they managed to identify several brand new examples of these SSD projective tensor products, which, I mean...
Which is a big deal, right? Like in the math world.
Oh, yeah, huge deal.
Okay, but why? Is it just about like adding more pieces to the puzzle, or is there something special about these new pieces?
It's more than just quantity, it's about the types of pieces they found. See, these examples, they're like rare gems. They each have this unique structure that gives us these valuable clues about the overall nature of these spaces. And get this, they even figured out these really specific conditions that guarantee the existence of these gems. It's like they have a treasure map that doesn't just tell you where to find gold,
Yeah.
but it tells you the geological formations that indicate its presence.
Okay, so they've hit the mathematical jackpot.
Yeah.
They're not only finding gold, they're figuring out how to identify gold-rich veins for future expeditions.
Exactly. Yeah, that's a really good way to put it.
So walk us through some of these gems that they found. What are these special Banach spaces called?
Well, one type they focused on they're called Rook-I spaces, which I know sounds kind of complicated, but stick with me.
Okay, I'm trying.
Okay, so imagine a normal graph, like the kind you used in algebra class back in the day.
Oh yeah, good times.
You probably plotted points on the X and Y axis, right?
Yeah.
Well, imagine a graph, but instead of just two axes, it has an infinite number of axes.
Okay.
That's essentially what an ax space is. It's like an infinite dimensional graph.
Okay, I think my brain just went cross-eyed trying to picture that.
It takes some getting used to.
Yeah, but what makes this infinite dimensional graph so special? What's the big deal about having, infinite dimensions?
So this is where it gets really, really mind-blowing. You see, a lot of the mathematical tools that we use for, like, solving problems they're designed for these finite spaces, right? Like things we can easily visualize and wrap our heads around.
Right.
But a lot of real-world problems, things like, predicting weather patterns or modeling how financial markets behave, they involve this just overwhelming number of variables,
Right.
essentially pushing us into the realm of infinite dimensions.
Wow. Okay, so these EP spaces, these
Well,
infinite dimensional graphs, they're like a bridge between that familiar world of like finite mathematics and then this crazy complex world of infinite dimensional problems.
You got it, yeah. They basically provide us with this framework for applying the tools and the insights from finite spaces to this much broader, much more intricate class of mathematical problems.
And that is why finding these new examples of SSD projective tensor products, especially in these spaces like ABA, it's a major breakthrough. It's like we're discovering this like whole new language that allows us to communicate with this whole new dimension of mathematical reality.
Exactly. Yeah, you're getting it. And what's even more exciting is that they didn't just stop at S spaces. They also explored this whole other kind of Banach space called a C0i.
A C0i. Okay, and what do these ones look like?
So imagine like a collection of echoes, but they're fading away.
Oh,
Each echo, it's a little bit quieter than the last one, right? Until eventually they just completely vanish into silence.
Okay.
That's basically what happens in a CRI space. You have this infinite sequence of numbers, but instead of them, continuing at the same level, they gradually fade away to zero.
So it's like the opposite of those like catchy tunes that get stuck in your head and just keep playing on repeat?
Yeah, exactly. These CRI spaces, they have this totally different flavor than those S spaces we were talking about before.
Okay.
But just like before, the researchers wanted to see, okay, if we combine these CRI spaces with other Banach spaces using those projective tensor products, are we going to end up with a space that has that special SSD property?
So do they strike gold again? Did they find those SSD gems when they were mixing in these fading echo spaces?
Yeah. They did, and this is where it gets extra interesting, okay? So they found that when you combine a COI space with certain types of finite dimensional Banach spaces, you actually end up with, surprisingly, an SSD projective tensor product. It's like you're mixing these two totally different ingredients, right? One's smooth, the other one's all bumpy and rough.
Yeah.
But then somehow you end up with this surprisingly smooth batter.
So it's not just about the individual ingredients, it's also about how you combine them.
Yeah.
Like how raw eggs and flour and sugar,
Yeah.
they might seem kind of gross on their own.
Yeah.
But then you combine them in the right way and boom, got yourself a delicious cake.
Yeah, that's a great analogy. And what makes it even more intriguing is that these COI spaces on their own, they're not naturally smooth spaces, right? They're more like, those bumpy dirt roads that rattle your teeth when you're driving down them.
Okay, yeah.
Blend it just right, and you get this surprisingly smooth ride.
I like it. These mathematicians are they're like culinary wizards, transforming these simple ingredients into something unexpectedly delightful. But speaking of delightful, I got to ask, how does any of this translate to the real world? We've been navigating this mathematical jungle, but what treasures are out there waiting for us outside of these abstract spaces?
Right. No, it's a valid question, and you might be surprised by the answer, actually.
Sure.
So while these concepts might seem kind of, confined to this theoretical realm, their impact,
Yeah.
it actually extends to some really practical domains, like take optimization, for example.
Optimization, like finding the most efficient route for my food delivery.
Exactly. Or imagine trying to find the absolute best way to schedule this really complex manufacturing process, or even optimize the performance of a financial portfolio.
Okay.
These problems, they all involve this huge number of variables, right?
Yeah.
And finding the absolute best solution, it can be incredibly challenging.
Yeah, I can imagine.
This is where understanding these SSD spaces, it becomes incredibly valuable.
So by venturing into the depths of these Banach spaces, these CRI spaces, these mathematicians, they might actually be laying the groundwork for smoother and more efficient solutions in fields like logistics, manufacturing, finance. Man, now that's what I call impact.
Exactly. Yeah, and it highlights this really crucial point about mathematical exploration in general, right?
Okay.
It often seems very abstract, very theoretical, but these explorations, they can have this ripple effect, often leading to these unexpected breakthroughs in other fields that then directly impact our lives.
It's like those historical discoveries in physics that seemed, purely theoretical at the time, but then they ended up revolutionizing communication or medicine years later.
Exactly.
Yeah, it really makes you appreciate the power of curiosity-driven research, even in the most abstract corners of mathematics. Speaking of exploring further, I noticed the paper, it mentions there's still a lot we don't know about these SSD spaces, and something called the LPP property.
Absolutely, yeah. While this research definitely uncovered some fantastic new examples and insights, it raised even more questions than it answered.
Oh, how so?
Well, it's like they've given us this map to this whole new continent in this mathematical world, but we've only just begun to explore its coastline. Yeah.
So much we don't know, so much uncharted territory. It's kind of exciting to think what other mathematical treasures are out there just waiting to be found.
It really is, and even though we've been spelunking through these really intricate mathematical concepts, there's this undeniable beauty to it all, you know?
Yeah, it really is like we've been exploring some hidden cathedral of thought with all these intricate theorems and proofs. They're like the arches and the buttresses.
And these new discoveries, they're like adding these new stained glass windows to this cathedral,
Hmm.
letting in more light, revealing new dimensions of its elegance.
I love that analogy. It
Uh-huh.
really it reminds us that even in this seemingly abstract world of mathematics, there's this real sense of wonder and artistry, you know?
Absolutely. Yeah, and it kind of underscores the fact that this pursuit of knowledge, whether it's in mathematics or science or art or any other field, it's a deeply human endeavor.
Yeah, it's about pushing the boundaries of what we know,
Yeah.
exploring the unknown and uncovering these unexpected connections.
And sometimes it's simply about getting lost in the beauty and complexity of the ideas themselves.
Well said. So as we wrap up our deep dive into this world of strongly subdifferentiable projective tensor products, what's the one thing that you hope our listeners they take away from this conversation?
You know, I hope they come away with this renewed sense of curiosity and a hunger to explore further.
Yeah.
You know, even if they didn't grasp every single mathematical detail, I hope they at least got a glimpse of the excitement, the wonder that fuels mathematical discovery.
Yeah, and maybe, just maybe, they'll be inspired to do a little exploring of their own. Who knows what hidden mathematical wonders are out there just waiting to be uncovered, right?
Absolutely. I mean, the,
Yeah.
the world is full of these fascinating ideas just waiting to be discovered.
Couldn't agree more. Well, that is going to do it for us this time. We'll see you all on our next deep dive.
Hey, everyone, and welcome back for another deep dive.
Today we're going to be tackling a topic that sounds a little intimidating at first.
It does sound a bit like a mouthful, doesn't it?
Yeah, strongly subdifferentiable projective tensor products.
Right.
It's quite a mouthful, but hopefully by the end of this, we'll all be saying it naturally.
I hope so too, and more importantly, understanding what it actually means.
Exactly, because it's actually a really fascinating area of math with some really cool applications.
It is, and you know, the core concepts here, they're surprisingly elegant once you break them down a bit.
Okay, elegant math.
Yeah.
I'm intrigued, so tell me a little more about this.
Okay, so imagine for a moment that you're trying to model a complex system,
Okay.
like say predicting stock market fluctuations. You're essentially working with a multi-dimensional landscape where each peak and valley represents a possible outcome, right?
Right.
Now imagine trying to navigate this landscape when it's full of jagged cliffs and sudden drops.
Okay.
That's what it's like working with mathematical spaces that are not smooth.
Okay. I think I see where you're going with this.
Yeah.
So if you're dealing with something that's not smooth, it's hard to find the best path or make accurate predictions.
Exactly. Strongly subdifferentiable projective tensor products, they give us the mathematical tools to kind of smooth out those landscapes,
Okay.
making it much easier to find optimal solutions to complex problems.
So we're like creating mathematical tools that are kind of like off-road vehicles for navigating these bumpy landscapes.
That's a great way to put it.
So instead of crashing into a cliff, we can smoothly navigate around it and get to our destination.
Precisely. And what's even more fascinating is that this research paper we're diving into today, it tackles a problem that has kind of stumped mathematicians for a while. It's like finding the missing piece of a puzzle.
Okay, so what is this puzzle exactly? What's the big question this research is trying to answer?
So in essence, they're trying to pinpoint exactly when a specific mathematical object called a projective tensor product
Okay.
is strongly subdifferentiable.
Okay, now that without getting too technical, what does strongly subdifferentiable actually mean in this context?
Yeah, it's a mouthful, right? But think of it as a fancy way of saying that this object has the desirable smoothness properties we've been talking about.
Okay, smoothness properties, got it. But why should I care if these mathematical objects are smooth or not? What's the real-world relevance here?
That's the beauty of it. This seemingly abstract concept actually has applications in a wide range of fields.
Okay, like what?
Like, let's take machine learning, for example.
Okay.
Imagine you're training an algorithm to recognize images.
Okay.
This involves feeding the algorithm massive amounts of data.
Right.
And it needs to find patterns and make connections in that data to accurately identify those objects.
Okay, I'm following so far.
Now, if the mathematical space where these calculations occur is bumpy or jagged, it becomes much harder for the algorithm to find those patterns efficiently.
Right, it's like trying to ride a bike on a bumpy road instead of a smooth paved one.
Exactly. You got it.
Yeah.
When these spaces are smooth, though, the algorithm can navigate the data much more easily.
It's leading to faster learning and more accurate results.
So smoother mathematical spaces equal more efficient algorithms.
Precisely.
That's really cool.
And that's just one example. These concepts also have implications for fields like signal processing, financial modeling, and any area where optimization is key.
Okay, you've definitely got my attention now.
Yeah.
Let's talk about what this paper actually discovered. What did the researchers find?
They made some significant breakthroughs, actually. They found new situations where these projective tensor products do exhibit the smoothness properties we want.
Okay.
And the way they did it is quite ingenious.
Ingenious. Okay, now you have to elaborate.
Okay, so one of the key techniques they used is something called reduction to finite dimensional subspaces.
That sounds a little complicated. It's actually not as scary as it sounds. Imagine you're trying to analyze like the acoustics of a vast concert hall.
Right.
Instead of tackling the entire space at once, right? You could break it down into smaller, more manageable sections.
Right.
That's essentially what they're doing here. They're taking these complex, infinite dimensional spaces and finding clever ways to analyze them by looking at simpler, finite dimensional pieces.
Interesting. So they're breaking down the problem into more manageable chunks.
Yeah.
But how does that actually help them prove anything about the smoothness of these projective tensor products?
That's where another clever tool comes in the modulus of convexity.
Okay. And what exactly is that?
So think of it this way. Imagine stretching a rubber band around different shapes.
Okay.
A circle being perfectly uniformly curved would offer like a consistent resistance.
Oh.
However, a shape with bumps and dents would result in varying resistance as you stretch that rubber band around.
Right.
The modulus of convexity is a way to quantify this resistance or curvature in a mathematical space.
So they're using this modulus to kind of measure how smooth these mathematical spaces are.
Precisely.
Yeah.
And in the paper, they focused on specific cases like a Rio,
Okay.
which is just a particular type of projective tensor product.
Okay.
And they proved that by carefully choosing the values of P and Y, they could ensure that this object had a high degree of smoothness,
Okay.
meaning a more consistent resistance when applying that modulus of convexity.
So by carefully selecting their mathematical parameters and using this measuring stick of convexity, they were able to demonstrate smoothness in these specific cases.
Exactly. And the implications of this are pretty significant.
Okay, I'm ready for these. So what's the impact of all of this?
Well, for mathematicians, this paper opens up all sorts of exciting new avenues of research in functional analysis.
Okay.
For instance, it provides new tools for understanding Banach spaces, which are these fundamental building blocks for all sorts of other mathematical spaces.
So it's like they've provided a new blueprint for mathematicians to work with.
Precisely. And when we have a deeper understanding of these spaces, we can develop more efficient algorithms for all sorts of things.
Like, give me an example.
Okay, take data analysis, for example.
Mm-hmm.
Imagine you're trying to analyze a massive data set
Okay.
to identify trends or make predictions.
Right.
The algorithms used for this often rely on navigating complex mathematical spaces, right? With these new insights into Banach spaces, we can potentially develop algorithms that can sift through this data much faster and more accurately.
So smoother mathematical spaces, thanks to this research, could ultimately lead to faster, more efficient data analysis.
Exactly, and it doesn't stop there. This paper also hints at something even more intriguing.
Hotel.
It suggests a connection between the smoothness of these projective tensor products and something called the LPP property for bilinear mappings.
Okay, I'll admit that one sounds a bit intimidating.
Let me try to explain it in a way that connects back to what we've been discussing.
Okay.
Remember how we talked about navigating those multidimensional landscapes and how smoothness makes that navigation easier?
Right, like in our stock market prediction example.
Exactly. Well, the LPPP property is a way to analyze how well-behaved certain operations are within those spaces. Think of it like this. You have a set of rules for moving around in that landscape.
Okay.
The LPP property helps determine how smoothly those rules operate, whether they lead to predictable outcomes or chaotic jumps and drops.
Interesting. So it's like having a reliable map and compass versus trying to navigate with no sense of direction.
Exactly. And what this paper suggests is that there might be a link between how smooth the landscape itself is, thanks to these projective tensor products, and how reliable our map and compass are, as described by the LPP property.
Okay.
It's like discovering a hidden bridge between two seemingly separate concepts.
Wow, that is fascinating. It's like this research is uncovering hidden connections in the mathematical world. So what you're saying is this paper is not only giving us these concrete examples of smoother mathematical spaces, but it's also suggesting this possible link between that smoothness and how reliable certain mathematical operations are within those spaces.
That's exactly it. And that's what makes this research so compelling. It's not just solving one specific problem, it's
Right.
opening up this whole new line of inquiry. It's like they've shown a light on a path in the mathematical jungle that no one's really explored before.
And what might we find down that path? What are some of the potential implications of this connection between the smoothness and the LPP property?
Well, for one, it could lead to a much deeper understanding of how these mathematical tools and concepts all work together.
Right.
Remember those more efficient algorithms we talked about?
Yeah.
This connection might allow us to design even faster and more robust algorithms by optimizing both the spaces and the operations within them.
So it's like we're not just building a smoother road, we're also fine-tuning the engines of the cars that drive on them.
A perfect analogy. And this has implications beyond just algorithms. It could impact how we model complex systems in all sorts of fields.
Like what?
Well, imagine being able to make more accurate predictions about financial markets or climate change or even the spread of diseases,
Okay.
all thanks to a better understanding of these mathematical principles.
That's incredible. It really highlights how, even in this world of abstract math, the pursuit of knowledge can have this really real and tangible impact on our lives.
Absolutely. And that's what makes this research so exciting. This paper, with its findings and its hints at even deeper connections, it's really just the tip of the iceberg. It's left us with more questions than answers.
Which I imagine for mathematicians is a pretty exciting thing.
Oh, absolutely. It's the best case scenario, really. It keeps us exploring.
Always learning. Well, I think we've definitely reached the bottom of our deep dive for today.
A huge thank you to you for illuminating this fascinating area of mathematics. And to our listeners, we hope this deep dive has sparked your curiosity and left you with some new insights to ponder. Until next time, keep exploring.